Great. So today I want to kind of continue on some of the things we discussed in the past few weeks and extend them to cases where the theories that we're deforming have supersymmetry. So to start, maybe just to motivate that proposal a little bit, let's kind of think about what was interesting about Tbar in the previous sessions and how this might generalize. So if anything, if we have any takeaways from the previous weeks, I think we've seen that the Tbar deformation in 2 dimensions is very magical. So in the first session, I think Jonah told us the original Zamolodchikov argument, which gives us this Berger's equation on the cylinder. Aurora showed us, among other things, this differential equation that takes us from the free boson to Nambu-Goto from Tateo and friends. Umang told us that in infinite volume in flat space, the Tbar deformation for a scattering matrix just turns into this momentum-dependent phase, like a CDD factor, and related this to random geometry. And Asrat told us about nice modular properties of Tbar deformed partition functions. So all of these are very nice properties of observables, things you can compute in Tbar deformed theories, but all of them critically relied on being in 2 dimensions, t equals 2. So you might ask, if we wanted to generalize Tbar to higher dimensions, is there any hope? What would go wrong? And you might think, okay, in the simplest case, we don't have to Tbar deform a CFT. You could Tbar a general QFT, but just for simplicity, what happens if you try to deform a CFT in bigger than 2 dimensions? So even around a conformal point, you immediately run into issues. So you can show basically just by conformal invariance that this combination of stress tensor correlators, which reduces to Tbar when d equals 2, but I've just written it in a more obviously invariant way. So this combination in d dimensions on the right side is proportional to something that looks like d minus 2 and then some position dependence. So the nice thing about d equals 2 was that this combination was independent of the distance between the insertions, x minus y, which let us define this nice local operator by taking x and y close, right? But when d is bigger than 2, the right side now does depend on position. So already around a CFT, it looks like it's hopeless that you would be able to define a local operator by taking some combination of stress tensors like this. And you might say, okay, what about this coefficient? Can you choose any coefficient, some relative coefficient between these two terms that makes that property work? And you can't. So for any choice of this relative coefficient, when d is bigger than 2, you're already in trouble. So why am I saying this? What does this have to do with supersymmetry, if anything?
Sorry, could I just ask?
Yeah, sure.
When people have talked about like this t-squared deformation, higher dimensions, is this the operator they're looking at, or is it slightly different?
Yeah, so this is the one, this coefficient, the 1 over d minus 1 is chosen for reasons from holography, like this t-squared deformation. People like to think about, I guess a d minus 1 dimensional bulk and then do some Wheeler-DeWitt with some radial evolution and argue that this should give Tt bar. So this coefficient is motivated from precisely that t-squared type proposal from holography. That's right.
Okay.
But for us, well, for me at least, I'm less interested in that because you don't get this factorization for free, right? You have to take something like a large n limit to get factorization, which kind of spoils the nice properties of Tbar in 2 dimensions.
Right, but this is the exact same operator that they look at. Okay.
Yes, that's right.
Thanks.
Hey, Christian?
Yeah.
Is anything known about 3-point functions of stress tensors?
Good. So you say, is there some combination that you could take with 3 stress tensor insertions that might be independent of position? That I don't know, but usually I guess the reason this is nice is because 2-point functions in the Tbar deformed case, you can prove you get some factorization of 2-point functions to 1-point functions. So I guess it would be more difficult to get 3-point functions to factorize into combinations of 2-point functions and 1-point functions. So naively, I would think it would be harder to get it to work by putting in 3-point functions, but that's actually a good question. I don't think anyone has actually looked at that I've seen.
Well, you'd also have the issue, if you want to define the composite operator, you'd have to take two of the points coincident, presumably replace it with the OPE. So you'd really be looking at a 2-point function of t with something else.
Yeah, that's right.
Yeah. That's what the something else's are that could appear there.
Yeah, but I mean, that shouldn't really be a problem if you think of, I mean, the OPE really should kind of just work. I don't know. I mean, anyways, just a question.
Yeah. No, that's interesting. I'm not sure, but good. Okay. So you could ask, can we put a little more meat on this observation that something seems to be different about d bigger than 2? And we can, so you can ask what goes wrong. So in any QFT in any number of dimensions, you always have some OPE, right? If it's not a CFT, you can't make any statements about radius of convergence and things like that, but there's always some OPE, now with no expectation values, just between these operator insertions, where you can write this guy with some coefficient again as some combination of operators with some coefficients. So the crux of what Jonah showed us in the first session was that in d equals 2, basically just translation invariance. I mean, the original Zamorodnikov argument also assumed rotation invariance, which would be basically boosts, but we're in Euclidean. But Cardy later showed you don't really need that. You can do this for non-Lorentz invariant theories. So in a nutshell, what happens in d equals 2 is translation invariance, which is conservation of the stress tensor, is enough to tell you that these coefficients A alpha are always going to be constants. So they're independent of the coordinate separation unless the corresponding operator O alpha is a total derivative, some d alpha of something. So that was a nice property of 2 dimensions. But when d is bigger than 2, just by kind of degree of freedom counting, this conservation equation is always just going to give you d independent equations for the d free indices nu. But the size of the stress tensor grows like d squared, up to symmetry, I guess. But the punchline is you're going to get fewer constraints from conservation when you go up in dimension. So basically that smaller number of constraints is insufficient to tell you that these A alphas are constant. They can diverge as x goes to y, even for non-derivative operators. So this is the crux of what goes wrong in d bigger than 2. So looking at this, you might think, okay, well, the only constraint you had was this conservation equation. So what if you could define some combination of operators, maybe some combination of more currents, which has more constraints, right? If you could increase the number of constraints, you might think perhaps there's some hope that you could constrain these A alphas to be, again, independent of position unless these guys are derivatives. So the idea that for maybe some people motivates supersymmetric Tbar would be that the supercurrent superfield, or the multiplet, contains the stress tensor, but it also has additional fields that have more constraints. So one reason for considering supersymmetric Tbar was that you might want to construct some combination of currents that is more constrained with the hope of getting a higher dimensional guy that could possibly have the same nice properties as Tbar. So this is really just speculation, but I wanted to say that at the beginning as a piece of introduction. So there's many ways to motivate supersymmetric Tbar. You might think that it could be connected to the superstring, since the ordinary Tbar gave us Nambu-Goto, or to brain actions, and those turn out to be true. But if you only care about Tbar and not these connections with string theory, I just wanted to present this little piece of motivation about possible higher dimensional generalizations that might motivate you to think about this question. Okay, so with the introduction kind of set, let me just lay out the roadmap for the rest of the talk. So in one line, the talk is that there's a natural analog of Tbar, which is manifestly supersymmetric and built from supercurrents. And that's what I'll tell you about. So to start at the beginning, really just to set notation, since I think everyone here probably knows supersymmetry, at least as well as I do, if not better. So to set notation, I'll just quickly review some aspects of supersymmetry that we'll need for the later discussion. In Act 2, oh, sorry, was there a question?
Yeah, I have a question. If you don't do supercurrent-squared, but just regular Tbar of a supersymmetric theory, does it break supersymmetry?
No, it does not. So that's a good point. Yeah, this. So I think David pointed this out at one point, that just because the supersymmetry in the original theory implies a degeneracy of the energy levels, and Tbar is not going to break that degeneracy between bosonic and fermionic states, supersymmetry will not be broken if you apply the original Tbar to it, but it no longer becomes manifest. So if you apply the ordinary Tbar to a SUSY theory, for instance, the supersymmetry transformations of the fields become corrected order by order in lambda, which makes it look kind of ugly if you just do it at the level of the Lagrangian. So one reason to do supercurrent-squared directly in superspace is that it manifestly preserves the supersymmetry, and you can see exactly what's happening at the level of the SUSY transformations. Yeah. Good. Okay. So so that'll be the kind of content of Act 2. Is this kind of manifestly SUSY, manifestly supersymmetric deformation, which is done in superspace, even though the ordinary Tbar does not break SUSY. And as we'll see, this manifestly SUSY deformation is actually on-shell equivalent to Tbar in 2 dimensions. So it's really the same thing on shell. It's just making it kind of a nicer presentation. And then in Act 3, there's a little more that I'd like to tell you that's related to d equals 4. So these will be some interesting connections between supercurrent-squared and nonlinear realizations of symmetries, or spontaneously broken symmetries, which allows us to make some statements in greater than 2 dimensions, even though those statements are going to be classical. Okay, any other questions or comments before I trudge on a little bit? Okay. All right, so I'll try to quickly review some of the pieces of supersymmetry that we'll need for this talk, but at a very high level, so what is supersymmetry? So in any theory with fermions, your Hilbert space splits into a direct sum of bosonic and fermionic pieces, which are basically determined by whether you have an even or odd number of fermions, or this fermion number operator. So in such a theory with fermions, we say the theory is supersymmetric if there exists an operator Q with the property that it sends the bosonic and fermionic spaces into one another, it squares to 0, and its anti-commutator gives you the Hamiltonian. So we say that each such Q is generating a supersymmetry, because one can show that if this anti-commutator property is true, it's basically a 2-line argument that this shows that Q commutes with the Hamiltonian. So these guys are symmetries, and they have associated supercharges which are conserved. So you could ask, why would one want to study supersymmetry? Even if you're not interested in theories that have supersymmetry at the end of the day, I think it's useful to study supersymmetry since it furnishes us with a large class of examples where one can make exact statements or do exact calculations. It gives a lot of control over the theory since you can do calculations using things like localization. So in some sense, this is kind of giving us a better way to understand quantum field theory at the end of the day, like a stable of examples in the same way as when you learn quantum mechanics, you study a lot of exactly solvable systems. Okay, so with that said, this statement, this definition here is for one supersymmetry. I could go through and put eyes on all of these guys. Later we'll have some cases with multiple supersymmetries. So if I have a collection of QIs, then the only thing I need to say is that now their anti-commutator has a delta ij. So if you have extended supersymmetry, you could have more than one operator QI with these properties, which we'll see later. It's relevant for us. Okay, so since this definition of supersymmetry is really a statement about the Hamiltonian, morally the Hamiltonian can be written as the square root of some fermionic operator Q, it would be nice to have an easy way to determine when Hamiltonians have SUSY, right? So the Hamiltonian has this nice representation as kind of I d by dt. So you might think, well, can we maybe invent some new auxiliary coordinates, some fictitious coordinates theta, with the property that these Qs also have nice representations as derivatives with respect to those new coordinates thetas. So if we do that, we might want to make Qi roughly a d by d theta, but in order to satisfy this condition that these guys anti-commute to the Hamiltonian, we have to add in a second term here, this theta d by dt. So if you choose the Qs to be of this form, then they satisfy the required algebra that they anti-commute to the Hamiltonian. Since the Qs are fermionic operators, this implies that the coordinates we're introducing, these fictitious coordinates, have to be anti-commuting. And since they're anti-commuting, each of them squares to 0. So any field which is a function of those thetas has a finite Taylor series expansion, right? This guy truncates at some maximum number of thetas, because if you have any theta repeated, it'll be 0. So this object that kind of packages together maybe some boson phi, some fermionic fields of the spacetime coordinate psi, and so on, is called a superfield, which is really just a container, right? So this is a bucket that you put a lot of fields in, bosonic and fermionic fields in. Okay, so that's a superfield. To be a little more concrete, in the rest of the talk, I'll focus mostly on 2 dimensions and n equals 2, 2 superspace. So this means we have really 4 Qs. 2 and 2 give left and right moving supercharges. And the nice thing about this construction in terms of these anti-commuting coordinates is that we have a simple criterion to tell whether a theory is supersymmetric. So for instance, if your Lagrangian can be written as a full superspace integral, so it's an integral over both the x and theta directions of some superspace Lagrangian A that can depend on some fields phi, then one can show that this is automatically supersymmetric. Where here I'm defining this integration over fermionic coordinates to be really the same as differentiation, that your integral is only 1 if your d theta matches the theta, and otherwise it's 0. And here the capital D that I've written here is this combination of fermionic and derivatives, ordinary derivatives, which is called a supercovariant derivative. Actually, I think I've written this for quantum mechanics where there's just a d by dt, but we can also do this in field theory, of course. And for chiral superfields, you can also add a half superspace integral. So these are kind of F terms that depend on some superpotential W that depend on your chiral superfield phi. Okay, so this is all special to our 2D n equals 2 that we'll be focusing on. A quick aside on notation. So in the second part of the talk, I'm going to use these complex anti-commuting coordinates theta and theta bar. So these are, I think, the conventions that we want, or that I used before, that these guys, the complex theta is some combination theta 1 minus I theta 2, and its bar is the bar. And we use the usual light cone coordinates x plus and minus, but instead of writing x plus and x minus, we write those coordinates with 2 pluses, so x plus plus and x minus minus. And this is really just to help us count spin for various operators, because the anti-commuting coordinates and fermions naturally have 1 index, 1 plus or minus. So we don't want to confuse kind of x plus with theta plus, since x plus or vector quantities with coordinates or components along the plus plus and minus minus directions are kind of different objects. So the plus plus and minus minus are really just telling us that these guys look like vectors, whereas single plus or single minus objects are spinors. So that number of pluses and minuses is helping us count spin. So for instance, the Tbar operator, which is some scalar combination of these stress tensor components, it will look like this combination T plus 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 plus, T minus 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 minus, and this mixed guy. And you can tell immediately that this guy is an overall Lorentz scalar because the number of pluses and minuses add up to 0. So then similarly, like derivatives like along x minus, the derivative with respect to x minus, we have 2 indices on to help us do that counting. And in these conventions, spinors will be kind of raised or lowered just with an epsilon. So the plus goes down to a minus, and the minus goes down to a plus. Okay, so with all of this kind of notational aside, let's actually make some statements about supercurrents. So we're trying to do TT bar in a supersymmetric way. So I guess the natural question you should ask is, if the stress tensor T is the Noether current for translations in a bosonic theory, can you find such a conserved current associated with translations in superspace? So the answer is yes. So under certain assumptions, so this is from Dumitrescu and Seiberg paper in 2011, but if you make an assumption that your multiplet contains both the stress tensor T and a supercurrent S, no other fields with spin greater than 1, and your multiplet is indecomposable. So indecomposable does not mean that the multiplet is irreducible. In general, the stress tensor multiplet will be reducible, but this means that it's not a direct sum. It doesn't split completely into a direct sum of submultiplets. But if you make these assumptions, then every 2-dimensional, or even 3 or 4-dimensional, in fact, every such supersymmetric field theory admits an S multiplet. So the S multiplet is a combination of, in this case, 3 objects, S, chi, and Y, with various spins. And that multiplet contains the stress tensor. So for instance, this object S plus minus, it contains a term that looks like a combination of the thetas, theta and theta bar, and the stress tensor with all matched indices, the plus plus, minus minus, and your chi and the Y will contain some terms that look like theta with the mixed indices. So plus plus and the minus minus. This is the plus minus, guys. So all that we're doing is really packaging the stress tensor and also some other objects, including a supercurrent S, into a multiplet of superfields which here satisfies some list of constraints. So this list of constraints here, which is just you know, some relations between the components of these superfields, if you write this out in components, it'll tell you that the stress tensor is conserved, that the supersymmetry current is conserved, and it'll also give you some other relations between the fields. So coming back to the original motivation, this additional list of constraints is what you might hope would give you some additional power, since it relates the components of these in a way that's stronger than just conservation. Okay. So this is kind of the result that we'll need to construct our SUSY Tbar. One additional aside that will be related later is on improvement transformations. So you may remember just from Peskin that even in a non-supersymmetric theory, your stress tensor is ambiguous in the sense that one can add improvement terms. So you can add an improvement term of this form, or this is one particular type of improvement, that's just some combination of derivatives of some scalar u. And if you do this, it maintains the symmetry and conservation properties of the stress tensor for any u. So for instance, when you find the stress tensor for Maxwell, you find out initially it's not gauge invariant, but then you can improve it into a form that is gauge invariant, which matches kind of the Hilbert definition of the stress tensor. And as an aside, this form of the improvement transformation is one reason why way back in the beginning, this coefficient 1 over d minus 1 is also interesting because this particular coefficient makes the combination on the left invariant under those improvement transformations, this particular type of improvement. Okay, so coming back, this type of improvement has an extension to the SUSY case, so the S multiplet can also be shifted in some particular way by some combination of superfields that depends on this real superfield U. And if you do this, the conservation equations and all of the constraints on the S multiplet remain unchanged. So we'll need this because, in particular, sometimes you can use this type of transformation. If you choose U cleverly, you can use this to set, say, chi to 0. You can transform chi to 0 and simplify your multiplet so it just contains, say, S and Y. So that, if you do that, is called the Ferrara-Zumina multiplet.
Christian,
Yes.
I'm a little confused by this improvement. So isn't the stress tensor defined by requiring it that it's the variation of the action with respect to the metric? So how do you, I mean, that's stronger than, I think, than just that it's, you know, conserved or whatever. So
Good. Yeah. So indeed, so there's a couple definitions of the stress tensor. So you could say that this guy, using the Hilbert definition, is basically ds dg mu nu.
Mm-hmm.
So this uniquely picks this guy out. Or you could just say that T mu nu is the Nerta current associated with translations, right? So if you start with a Nerta current and say, I'm just going to run my Nerta procedure on the Lagrangian, this procedure is more ambiguous than the Hilbert procedure, in fact. So if you say T mu nu is the Nerta current, then this actually only defines a class of transformations under which you're free to add a particular ambiguity. So indeed.
So you're using this second pink definition.
That's right, yeah. So this guy, which we just say, I have some symmetry under, say, space-time transformations. The current associated with the particular symmetry is ambiguous, but the linearized response to a fluctuation in the metric is not. I agree. So only if you're using the Nerta definition are you free to make this class of improvements. That's right.
So wouldn't you just take the green to be the stress tensor? So yeah, I guess maybe we're just not calling this thing the stress tensor. We're just calling it some object that's appearing in your calculation then, or something.
Well, yeah, you could. I mean, in the bosonic Tbar, it often doesn't matter. So in the bosonic Tbar, you can say, I'm going to take my definition of the stress tensor to be Nerta, right? So you could say, to be Hilbert. So in that case, you could say, I want it to be this. And then there's no ambiguity and everything is fine. So in that case, you can take this to be the definition. In the supersymmetric case, there's some subtlety because when you say I'm going to fluctuate my superspace Lagrangian with respect to some supergravity fields, there are several different formulations of supergravity. So this, even the Nerta definition of the stress tensor has some slight ambiguity in the case of supersymmetry because there's different ways to formulate supergravity. And as we'll see, that ambiguity actually corresponds to this type of improvement transformations in the S multiplet. So yeah, I agree. It kind of trivializes for bosonic gravity, but it becomes somewhat more interesting for supergravity, I guess is the punchline.
Okay, I would like to understand that better, but I won't hold this up anymore.
Okay, I'll say a little bit about it more later, but only kind of schematically. But um, good. Okay, so yeah, I think the takeaway here is that if you don't use the Hilbert definition, even in the bosonic case, there's some ambiguity under improvements, and that looks in the supersymmetric context like this combination here, which we'll use in a moment. Okay, good. So that's our lightning review of supersymmetry. The punchline being that there's this nice guy, the S multiplet, that extends the stress tensor to a collection of superfields. So now we can ask the question, is there a way to combine, for instance, the objects appearing in the S multiplet into some combination that looks like Tbar? So yes, the answer is yes, and I'll just write it down. So in the case we're focusing on, say for 2-2 supersymmetry, if you have an S multiplet that contains those three fields, the S, chi, and the Y, then we can define a Tbar type deformation, a super Tbar deformation, using this equation. So the Lagrangian flows by this calligraphic Tbar, which is really the combination you get by just contracting all of the indices in the S multiplet fields. So as we saw, when you kind of pair these guys so that all of the pluses are paired with minuses, that's effectively taking some contraction, some Lorentz invariant contraction of all of these superfields. And then I put in some superspace integrals over those contractions in such a way that we're left with some bosonic Lagrangian. Okay, so you can ask, what are the properties? Well, this is, again, a deformation constructed out of bilinears of currents, just like the usual Tbar. And in fact, one can show after a fairly laborious calculation that in 2 dimensions at least, when you impose the equations of motion and integrate out all of the components of these superfields, this guy reduces to Tbar plus the equations of motion terms which vanish, and plus some total derivatives, which are going to, we can discard if you're integrating over infinite volume, for instance. So in 2 dimensions at least, this supersymmetric version of Tbar is actually equivalent on shell to the usual Tbar, which is kind of a reflection of the fact that, as Jonah asked before, the usual Tbar preserves SUSY. So you might think that a manifestly supersymmetric version of Tbar should morally be doing the same thing. And in this sense, it kind of is. But the superspace formulation makes it totally clear that this guy is preserving SUSY, and it makes it clear how the SUSY transformations will act, even in the deformed theory. But as we'll see in 4 dimensions, this is not true. In 4 dimensions, the supersymmetric Tbar is genuinely different from the ordinary Tbar, which might give you some hope that it has different point splitting properties, that it might be well defined by point splitting. But okay, so maybe just to give a little kind of overview of the properties of this guy in 2 dimensions. So as we saw in, I think, Jonah's talk about the Zamolodchikov-Smirnov, the 2016 follow-up. So there's a broader class of operators besides just Tbar that look kind of morally like AS, and then maybe A prime S prime of X minus some other operator BS plus 2 of X, and maybe B prime S prime minus 2 of X, where S is some spin. And these operators, where S equals 0 is the usual Tbar. But this entire class of operators for other S can be shown to be well defined by point splitting by a generalization of the 2004 Zamolodchikov argument, really just using conservation, where these A's and B's are currents. But the nice thing about this supersymmetric Tbar that we just defined here is that it's still well defined by point splitting, but it's not of this form. It's not of this Zamolodchikov-Smirnov form. So the proof in the 2-2 paper, our proof that this is well defined by point splitting is actually totally independent from the logic of the Zamolodchikov-Smirnov paper, which again is nice because you might hope that that type of argument generalizes to higher dimensions, possibly with more supersymmetry. So the argument is a bit technical. There's a lot of steps that basically just you take the point split operator and just do a lot of computation. But the upshot of that calculation is that if you take your point split operator by taking each of these products of currents, so the SS and also the chi-chi and the YY that we showed before, and just insert them at different points x and x prime. And then all you do is take a derivative with respect to, say, x or x minus x prime, if you like, of this operator and just compute. You show that this thing reduces to equations of motion plus some overall translation, some P, some momentum generator, acting on some fields, and some overall supersymmetry transformation, some Q, acting on some fields. So this combination is really an overall superspace derivative, an overall space derivative and some overall superspace derivative, which means that this thing is indeed well defined by point splitting up to equations of motion, which will vanish inside of correlation functions, right? Some derivatives, for instance. Okay, so super TT bar is well defined for this reason. You could ask, what about deformations of nice Lagrangians, like how Aurora showed us that the Nambu-Goto arises as a deformation of the free boson. So we could also do that sort of calculation in superspace, which I'd like to just briefly sketch, and this will tell us a little bit more about this question about the different supergravities as well. So just to get the flavor of the calculation, if we start with a chiral superfield, so this free superfield capital phi, whose superspace Lagrangian is just phi bar phi, just to kind of ground ourselves and remind us of what this means in kind of the ordinary bosonic Lagrangian. So the components of the superfield phi, kind of written out explicitly, are just a complex scalar field, lowercase phi, some Dirac fermions, psi plus and psi minus, and some auxiliary field f that will appear here. So this capital phi is just a bucket that contains these bosonic and fermionic fields. And if you took this Lagrangian up here and did the superspace integral, just integrated out what this means, you would find that this undeformed Lagrangian before doing TT bar just looks like this at the bottom. So f squared just appears here by itself, which you could integrate out using its equation of motion. The equation of motion is just f equals 0. So you can see that we're just really starting with a free complex boson phi and these free fermions, the psi plus and psi minus. So this is really just a fancy way of writing the complex scalar and the two fermions, the psi plus and psi minus. Okay, so how does one deform this? So I told you that this field should have an S multiplet, but you could ask, how do you actually obtain the expressions? How do you obtain the components of that S multiplet? So this is where we have to do a little bit of supergravity to actually find what the expressions for those superfields are. So this is kind of getting to Gautam's question. In a usual bosonic theory, the stress tensor T mu nu, you could either find up to some ambiguity, you can determine T up to the Nerta procedure with that improvement ambiguity, or you could obtain it uniquely as the linearized response to metric fluctuations. You could say that my T is uniquely the guy that couples to the metric in this kind of Hilbert definition. So both of those procedures generalize. So you can find the supercurrents either from a superspace Nerta procedure, which was studied in some generality in 2001. And this is actually what we used in the 0-1 and 1-1 cases. We just used this Nerta procedure directly. And it turns out that with no improvement transformations, just the naive thing that you get just directly works. But for 2-2, things are more complicated. If you use the Nerta procedure, it seems that you have to come up with some sort of improvement transformation to get the right notion of the stress tensor. So as Gautam alluded to, maybe it's better in that case, instead of dealing with that ambiguity, to just say, well, I'd rather just couple to supergravity because that thing seems like it's going to be less ambiguous. But the only issue is that just as there's these different notions of multiplet, so the S multiplet can be improved, say, to the FC multiplet, there are also different notions of supergravity, even in 2 dimensions. So one of them is what's called the old minimal supergravity. So there's an old minimal supergravity whose degrees of freedom are these pre-potentials, H++ and sigma. So sigma is a complex superfield, excuse me. And these things are called pre-potentials basically for historical reasons. Schematically, what's going on here is that in 2 dimensions, we have really my degrees of freedom are something like a super Vielbein. So there's an EA M, if you like, and some supersymmetric version of a spin connection, so some capital omega, say ABC. So these are my guys that determine, say, some supersymmetric version of a curvature, like an R. So these are my real degrees of freedom, but for two-dimensional supersymmetry, the superveilbein and the spin connection are constrained. And because it's difficult to deal with constrained fields, it's often easier to parameterize the solutions which satisfy those constraints and just work with the unconstrained fields. And one way of parameterizing those unconstrained fields are these objects H plus minus, and the sigma. So kind of morally what's going on is these pre-potentials at the top, the H plus minus, and sigma, those things determine a Vielbein and super spin connection, if you like, that satisfy the supergravity constraints. And in turn, those guys determine a curvature, which is kind of the physical object that, that kind of couples to the supersymmetric stress energy. So this is why these are called pre-potentials, because if you like, you can think of the Vielbein as kind of morally like a gauge field, and the curvature is morally like a field strength. So if you like, that's kind of saying that the Vielbein is morally like a potential. So these objects at the top that determine the potential are in some sense a pre-potential. So this is just kind of the reason why this term exists. But the upshot is that this formulation, the particular formulation that we use here in terms of H and sigma, is not unique. So H and sigma couple to the FZ multiplet. If we had used a different formulation, for instance, one called the new minimal supergravity couples to a different stress energy multiplet called the R multiplet. And the general S multiplet couples to something called the non-minimal supergravity. So there's a collection of supergravities and an associated collection of stress energy multiplets. And for a given theory, depending on whether you can use an improvement transformation to set one of these to 0, there may be some freedom or some ambiguity in which of these formulations you want to use, which is maybe a quick summary, but that's kind of the heart of what's going on here. So for the example that we're considering, this free chiral superfield, there's actually a nice freedom. So in this case, we can actually go to the FC multiplet. We can kill off one of the degrees of freedom in the S multiplet with an improvement transformation. So if you do that, if you make that transformation, then the only objects remaining in your stress tensor multiplet are the S, which we now call the script J in the case of FC, and the Y, which you can write as a derivative of some scalar V. Okay. So if you do that, then just in the usual case, as when you vary the Lagrangian, there's a term that looks like the stress tensor contracted with your change in the metric to get your Hilbert definition of the stress tensor. In this case, if you vary the superspace action, you get a guy J, which couples to the pre-potential H, which again is related to the Vielbein or the metric, and you get this guy V, who's coupling to the sigma. So roughly the J and the V are like the stress tensor, and the H and the sigma are like the fluctuation in the metric. Okay. So this probably just gives a kind of flavor of the calculation without a lot of the details, but if you use that FC formulation, you can show that the super Tbar flow equation that we wrote down reduces to this kind of nicer form that's all a full superspace integral of this JJ and VV. And then you can just compute. So you fluctuate the superspace Lagrangian, and you find that to leading order, well, the V is 0 at leading order, and the guy who couples to the J, J that couples to the H is just this expression, this D plus phi and D bar plus phi bar. So you get a leading correction to the Lagrangian, which just looks like this. It's a 4 fermion term with these d phis and d bar phis. And then you can make an ansatz for the all orders and lambda result. So you just make an ansatz that this guy at all orders looks like some function times this 4 fermion term, where the function has to depend on these scalar combinations of some derivatives of your superfield phi. And you could just get a differential equation and try to solve for that function f. So this is kind of like the superspace version of the Tateo paper, finding this function f that turns out to be Nambu-Goto. Okay, so kind of skipping some of the details, you can simplify this question of finding the function f because at any lambda, the equations of motion will tell you that one of these combinations of the fields y has to vanish. So this y vanishes on shell, which means that you could really just get this as a function of the other combination x, and after some slogging, you get this result. So you get this kind of nice looking square root structure in superspace where you have the free action plus a 4 fermion term that has the square root type structure. And these a's and b's in the bottom are just combinations of the ordinary coordinate space-time derivatives of the superfield phi. And for instance, one can show that if you truncate to the bosonic sector, sector of this is really just the Nambu-Goto Lagrangian for a complex scalar, so for phi. So this is the superspace version of the deformation of the free boson going to Nambu-Goto in this nice supersymmetric Nambu-Goto form. Okay. So that's kind of one of the main results of the 2-2 paper. I just want to flash a couple of related results very quickly. Some things that built upon this result and the other results for the 1-1 and the 0-2 that some of our collaborators worked on. So Friedman and friends had this kind of alternate procedure for generating the SUSY Tbar deformed actions from a topological gravity type argument. So this gives a nice algebraic procedure that agrees with our Lagrangian and has this interpretation as a sort of half diffeomorphism. And when you integrate over some half diffeomorphisms for this Vielbein E that they couple to. This Fotis-Varakis and friends showed that this Volkov-Akulov action, which I'll say a bit more about in the last part, is related to spontaneous SUSY breaking and is in fact itself a supercurrent-squared deformation. So that's related to these statements about non-linearly realized symmetries that I'll say a bit more about. So this other group also computed correlation functions to leading order around a superconformal field theory. So this is kind of morally like the super version of Cardy's paper on Tbar deformed correlation functions. And also our super Tbar has been extended to super J-Tbar by one of our collaborators and friends. So this is kind of the state of the art of supersymmetric Tbar, some of the recent results on this.
With the J-Tbar, do you just need, all you need to add is a U1 for the super, or do you need some extra symmetry besides the U1?
That's right, you just need the U1, but the U1 will itself complete into a superfield in the same way that that T does. And then you can make some superspace combinations of those, which is kind of in the same sort of schematic way that we do with the T.
Okay.
Good, okay. So the last part, I have some somewhat more recent results that relate to kind of these nonlinear realizations, but any other questions or comments about the kind of setup for the deformation and this 2-2 example? Okay, good. So one kind of simple motivation, I guess, for this relationship to the nonlinear realizations. So as Aurora, or originally the Tateo paper that she showed us a couple weeks ago, told us, the Tbar deformation of the free boson gives us this kind of Nambu-Goto or Dirac type Lagrangian that has a square root. But this action has been studied in detail. So this action actually has a nonlinear shift symmetry. So in the simplest case, the shift symmetry looks like this. More generally, if you have a collection of phi i's, the shift symmetry looks like delta, some parameter epsilon, in two different directions, which I'll call b and I. It's a combination of terms that has some, so there's a delta b mu, and then say one phi I, and there's a delta I mu along one of the directions xb, where here the phi I depend on some coordinates xb, and then there's the nonlinear term, the phi I db of phi mu. So this reduces to this case where this last term, the phi d phi piece, is this piece in this simple case. So this is a kind of strange looking symmetry for this Nambu-Goto or Dirac type action to have, but it has a simple interpretation. So if you take, say, a string, if you put a long string just embedded in some d-dimensional space, the original d-dimensional space has Lorentz invariance, but this is singling out some sort of submanifolds, right? Some submanifold with one space and one time direction. So that straight string is going to break your isometries in the bigger space to some subgroup that preserve the location of the string, for instance. So that breaking, that spontaneous breaking of the Lorentz symmetry in the parent space, we expect to give us some collection of Nambu-Goldstone bosons, right? D-2 of them, in fact. So those Nambu-Goldstone bosons are the fields phi I, and this breaking pattern is exactly what determines this nonlinear shift symmetry. So you can think of this symmetry as really descending from Lorentz invariance in the parent space, where if I have some symmetry that rotates one of my transverse directions, so if I have a transverse direction, say phi, and some direction along the string, which is maybe x, then I should have some symmetry which rotates phi into x, but doing that rotation would break, say, a static gauge condition. So in static gauge, we typically say directions along the string are identified with these spacetime coordinates, and this would be broken in such a way that needs to be repaired with a diffeomorphism. So that combination of a rotation plus a diffeomorphism that restores static gauge has exactly this action as a nonlinearly realized symmetry. So you might ask, okay, something is strange because we get this Dirac type action, this square root structure out of Tbar, and the square root structure has this highly non-trivial nonlinear shift symmetry which is descending from Lorentz. So you could ask, is there something more general going on here? Does Tbar or its supersymmetric generalization lead to these nonlinear realizations in other contexts? And it would be especially nice if we could do that in more than 2 dimensions, since usually our Tbar discussion is limited to 2 dimensions. So I'll just flash a few results for you where we can show that that is true. So one of them is in 4 dimensions using the FC multiplet. So it's the first time we can say something about t greater than 2, which is nice. So for instance, if you have a 4-dimensional n=1 theory, and this guy has an FC multiplet, which is again some simplified version of the S multiplet, where you improve one of the terms to 0. So the guys in the FC multiplet in 4 dimensions are typically written as J and X, and they satisfy some conservation equation. Then we propose we can write down a 4-dimensional supercurrent-squared operator, which again comes from contracting the indices on these guys in some way, and with some coefficients. So the coefficients are chosen in a particular way to make something nice, some nice properties, which I'll say on the next slides. But I first just want to comment that even though the 2-dimensional supersymmetric Tbar turned out to be equivalent to the ordinary Tbar on shell, this is not. So it's not for 2 reasons. One is that if you take this supersymmetric Tbar and integrate it out, it has, among the contributions, a combination of stress tensors plus other junk, but this combination of stress tensors is not the combination of stress tensors that would be proposed from this holographic context, because in that case, this relative coefficient was 1/d-1, which would here be a third in 4 dimensions. So this is already inequivalent to these other proposals for Tbar because of this different coefficient. And as a side remark, the other choice of coefficient made this invariant under improvement transformations. This choice of coefficient is not invariant under improvement transformations, but it only shifts by a constant. So if you improve the stress tensor, this combination only picks up an overall constant, which looks like a cosmological constant, but if the theory is not coupled to gravity, then it's not going to affect the dynamics. It's just a shift in the Lagrangian. So this is one reason why it's not equivalent to this other proposal for Tbar, but more importantly, there's other contributions.
Sorry, can I ask a question about that cosmological constant thing?
Yeah.
Because you're adding this constant kind of like infinitesimally, right? Like at each step you deform. I vaguely remember like Eva Silverstein's group with the DS stuff where they have like a Tbar plus some constant term. They argue because of that the way you deform that it does more than just like it actually does have an effect on the overall Lagrangian. what,
Right. In that
so,
case,
so
I
why
think
does it not have an effect here if it does there?
good. I think for Eva, so Eva, I think if I remember correctly, Eva's deformation had 2 steps. So you kind of first deform a little bit by just TT bar. So you first go from the seed theory by TT bar, some step lambda, and then after that you deform by a combination that's just you continue TT bar, plus you add a cosmological constant capital lambda, which is correlated with the TT bar parameter little lambda, right? So I think if you do this, the Eva deformation, since you're first doing pure TT bar and then doing this combination in a coupled way, the lambda, the cosmological constant lambda, is going to couple to TT bar in a different way than if you had just added a constant in the seed theory and deformed, right? Because if we added, for instance, if we took the free boson d phi squared.
Sorry. Like, but yeah, okay, you're only adding a constant in the seed theory. You wouldn't be adding it at every step.
Oh no, you're right, actually. Sorry, this would indeed, at every step, you'd be adding a constant to the TT bar deformation. That's right. So it would really look like the flow equation would be d Lagrangian d lambda would be the old TT bar plus a new constant, say k or something. So
Yeah.
this k, indeed, so this k would change something. Why does that not? I think the point would be that even though we're adding this at each step, would it be true that at the final step after you solve this flow equation that there would be a final constant k? No, it seems like it would. Okay. Infinitesimally, at least, adding just this constant k, it seems like would be equivalent to doing nothing. But then as you go to the next step, I think that k would couple back into the TT bar. That's right. Good. Okay, so I'm not sure. Yeah, I think the statement that this picks up this k under an improvement actually maybe is somewhat non-trivial. So that improvement would change the flow. So there is a particular choice, and improvements would change the results, I think. In practice, for the 4D cases, we'll just couple to supergravity, which again eliminates this ambiguity due to the improvement. But I think I agree with you that yes, doing an improvement would actually affect the results in a non-trivial way when you go to a finite step in the flow. That's right. Good. Okay, but at the level of differences from the other higher dimensional proposal for TT bar, in addition to the different coefficient, this deformation includes additional contributions which will not vanish on shell. So the FC multiplet in 4 dimensions, besides the stress tensor, has some other objects. So it has this vector J mu, it has a complex scalar X, and these things in general won't vanish. So this thing is adding additional contributions to the usual TT bar. And one might hope that the additional contributions from these things would have extra effects when you take the point splitting limit than the ordinary combination of stress tensors, which is known to be regulator dependent. So I should just flag that we don't yet know whether there is a proof for this operator that you can run all of the usual Zamolodchikov arguments for point splitting and things like that. But to kind of motivate its interestingness, that it does have some nice classical properties, I'll just flash a couple of results that show that this deformation is related to a few interesting actions, and that those actions have these nonlinear realizations, just like Nambu-Goto. Okay, so one example is this Goldytino action. So in the same way that if you spontaneously break Lorentz, you get a Nambu-Goldstone boson, or more generally, spontaneously breaking any bosonic symmetry like this will give you a Goldstone. If you spontaneously break SUSY, you also get these fermionic degrees of freedom, which are called Goldstinos. And those Goldstinos will generally have some action which is prescribed by the breaking pattern. So one concrete example that we can write down, so this is the Komargatsky-Seiberg model for this Volkov-Akulov action, which is in 4 dimensions when you break specifically n equals 2 to n equals 1 supersymmetry. One way of writing the action for that fermion, so this psi is your fermion, which is the Goldstino, looks like this. So this is just the action for the fermion, but it has this kind of kinetic looking term and then a set of interactions. So some psi squared interactions and then this 4 psi term. and then it has to truncate at this because after this, all higher terms would be vanishing. So one result, oh, sorry, was there a question?
Yeah, just a quick question. You might have said this before, but is there a charge or some quantity that labels the sectors after this breaking? Or is there, yeah, that's.
Let's see, the sectors after you break. So
like the, like the Higgs VEV, I guess, would be if we're spontaneously breaking or.
Oh, good. Yeah, yeah. So typically you would do this breaking by turning on some condensate, for instance, and here this parameter f. So I don't think f is exactly the condensate, but f here is some parameter which indeed would label those sectors. So f is kind of a number which is parameterizing, if you like, either the sector or the scale at which the SUSY breaking is happening. That's right.
Okay, thanks.
Good. Okay, so the upshot, I guess, is that this presentation of the Goldytino action itself descends from a supercurrent-squared flow. If you write this in a manifestly supersymmetric form, we show in the spontaneously broken, or the nonlinear realizations paper, that this action descends exactly from a supercurrent-squared flow, and the flow parameter lambda is related to 1 over f squared. So this is really a Tbar flow where this constant term looks like kind of 1 over lambda, and these other terms kind of are like a lambda squared and a lambda cubed piece. And this looks very similar, I guess, in the bosonic sector to when you Tbar deform the free scalar and get Nambu-Goto. It really looks like 1 over lambda times some square root, 1 plus lambda d phi squared minus 1. So in the bosonic sector, you have this kind of infinite constant, this minus 1 over lambda, that there's been some papers about. One of our collaborators wants to interpret this infinite constant as a sort of target space B field, but that infinite constant also appears in just the fermionic sector, right? So there's kind of some parameter here that's blowing up as lambda goes to 0. So this is one example, this Goldytino, and this 4D result extends the 2D result that I alluded to earlier, the Ferraco's paper, where they did this for 2-dimensional Goldytinos. Another nice example is for gauge theory. So if you think of a supersymmetric version of kind of Maxwell, you could think of a field strength. So you take your field strength F for ordinary Maxwell and put it in a superfield W, roughly speaking, and this thing gives you a supersymmetric theory for an n equals 1 vector multiplet, which looks like this. It's basically the W squared integrated over 2 thetas plus its conjugate. And as we show in this nonlinear realizations paper, if you deform this theory by supercurrent-squared, kind of the super Maxwell, you get again a form that looks almost exactly like the super Nambu-Goto with the square root in the bottom. And this is known to be one presentation of the supersymmetric Born-Infeld Lagrangian. So this is a deformation of Maxwell, which in particular has a second non-linearly realized supersymmetry. So I think this was pointed out by Bagger and Galprin in '96, but even though we've written this theory, the way I've written it here only has a manifest n equals 1 supersymmetry. This theory has a second hidden supersymmetry under which the field strength transforms in some way. So I've written the transformation here, but the takeaway is just that when W transforms in this way, X is some field which determines the Lagrangian, and if you work it out under this transformation, X transforms in a way that looks like W contracted with some parameter, your second SUSY parameter eta, and that is a total derivative. So the Lagrangian changes by a total derivative. So the interesting feature here is that this the super Tbar deformation is in some sense enhancing your supersymmetry, right? You had a theory starting with n equals 1, and you apply super Tbar, and you end with something that has secretly n equals 2. And it does it in a way which is sort of unique, right? In the Bagger-Galprin paper, you could ask, under some conditions, is the Lagrangian that has a second non-linearly realized supersymmetry and reduces to this theory for the n equals 1 vector multiplet field strength, is that unique? And indeed, it's more or less the only action that has that second non-linearly realized supersymmetry and is consistent with the constraints on this W. So it seems like there's some rather deep connection between Tbar and its supersymmetric generalizations and these non-linearly realized symmetries, or equivalently spontaneously broken symmetries, which remains to be explored. Okay. So I'll just say that, I mean, I'm speculating wildly, but it seems that there's a deeper story going on here with the nonlinear realizations and also the questions about whether you can get well-definedness and the other Tbar-like properties to work in higher dimensions, but it's an open question for future work. With that, I think I will stop and take other questions if there are any.
I had a question that you might already have answered. I missed a little bit. So these symmetries, these non-linearly realized symmetries are kind of emergent in the UV. So is there a sense in which you know the relevant deformation that would break it and take you back to your starting point?
Yeah, in some sense, it's kind of funny because they emerge, I guess, when you add Tbar. So when you turn on lambda, I guess this, for instance, in this case, just the nonlinear shift symmetry. So if you add lambda, then the symmetry gets turned on. So in the sense that adding lambda and adding Tbar is flowing up the RG, I mean, it's really not a conventional RG because you're going to a theory which is known to be non-local. But in that sense that turning on lambda activates this nonlinearly realized symmetry, you would say that, well, okay, reversing Tbar, so flowing towards smaller lambda, which is going back to the undeformed theory, it would turn off the symmetry, right? So if you flow to the IR in the sense that you're taking lambda smaller and smaller and going back to the undeformed theory, then this nonlinear shift symmetry would go away or reduce to one of the theories of the free boson. I'm not sure if that answers your question.
Yeah, I think it is. So you're saying when lambda becomes small, it coincides with an already existing symmetry of the free boson?
That's right. So this would, I think, turn into just kind of a shift symmetry of the free boson in the sense that that constant velocity solutions are solutions for the free boson. So this kind of linear shift symmetry when lambda equals 0 kind of is deformed in some sense to the nonlinear shift symmetry at finite lambda. That's right.
So maybe there's a sense in which the algebra it's some contraction of the algebra or something.
It could be, yeah, since I guess at finite lambda, this is just, you can show that the algebra of these nonlinear shift symmetries is really just Lorentz. It's a nonlinear realization of Lorentz. So when you, right, it may be that when you deform it, it just turns into the linear realization of Lorentz in the other directions, right? Because kind of pictorially, when you take lambda to 0, this is just taking the string which is breaking some isometries down to a particle, the free boson, which has the full linearly realized Lorentz.
And another question. So so far this connection between Tbar and nonlinear realized symmetries is mostly empirical. You're saying you have a bunch of examples where it happens.
That's right. Yeah.
Okay. And the number is there? Do you have an understanding of the number of nonlinearly realized symmetries as a function of? Is it like, you know, the number of fields in the IR or something like that?
Right. It does seem, since you could have rerun Tbar with kind of the n bosons, I guess, like phi I. And in that case, the number of free bosons phi I when you deform is going to turn into roughly the number of transverse directions. So the breaking pattern basically in 2 dimensions would only be dependent on the number of bosons you have when you go to the IR. But when you have more kind of almost like world sheet directions, right? If you have a collection of X in 4 dimensions and a collection of fields, either kind of these bosons and fermions in the Goldytino case or the gauge fields in this case, here I don't have an answer for how to predict what the symmetry enhancement pattern is going to look like. I mean, really here we only have the 2 examples, I guess, of the Goldytino and the n=1 to n=2 in Born-Infeld. So here, I mean, I'm sure it's a function of the number of degrees of freedom in the IR and kind of the number of coordinates, but it's not clear what the precise map is.
Okay, thank you.
Hey, so I'm still a little confused about how the ambiguity of the stress tensor. So so you mentioned the 2 definitions. So if I have field theory coupled to gravity, it's very important that the stress tensor be unique, right? Because then because gravity doesn't couple to the derivative of the stress tensor, gravity couples directly to the energy. So in this whole story, you haven't coupled to gravity at all. So I guess there could be this ambiguity, but in supergravity, uh, uh, well, how do you get around this statement that gravity, I mean, it should be a unique object. I'm confused as to why it's not a unique object whenever we couple to gravity.
Why the stress tensor multiplet itself is not unique?
Or whatever expression you have for the stress tensor, I would assume that it should be unique just because if you couple to gravity, gravity couples to energy, not gradients.
That's true, but I think this might be an artifact of the fact that we're really coupling to linearize gravity around flat space, right? So at the end of the day, we're really just using the coupling to gravity in order to extract components for the stress tensors, right? Rather than in some dynamical gravity background. But I guess even around a non-flat background or with dynamical gravity, there's, I think, no ambiguity in physical stress energy as far as supergravity. It's really the statement that there's different ways that you could formulate the couplings between the supergravity multiplet and the stress energy multiplet. So in theories where you have both a well-defined FC multiplet or an R multiplet, for instance. So you could either choose to parameterize the couplings between the gravity fields and the matter fields using the R multiplet and new minimal supergravity, or you could parameterize them using the FZ multiplet and old minimal supergravity, and the equations will look very different, but the dynamics, I think, have to be the same. So I think really this ambiguity is more about the degrees of freedom you're using to describe the dynamics than the dynamics themselves, if that makes sense.
I see. So you're saying the exact actual expression for the stress energy is not, is not ambiguous anymore in supergravity, but I guess the way you represent it in terms of these multiplets is?
I think that's true, because at the end of the day, if you had integrated out in superspace and looked at the bosonic degrees of freedom alone, there would be some unambiguous Hilbert stress tensor, right? You would have some collection of scalars and maybe fermions and vectors or something, and those couple to the metric in some, perfectly well-defined way, right? You could fluctuate with respect to G. So I think the ambiguity is really just in going to an off-shell superspace formulation of supergravity, and that introduces some ambiguities, right? Because when you want to formulate, say, two-dimensional off-shell supergravity, there's a few ways to do it that a priori look very different. But I agree, physically there's one Hilbert stress tensor not in superspace, just in spacetime. And all of these formulations have to be equivalent with what you would get by integrating out and using the usual Hilbert stress tensor.
I see. Okay, that makes sense.
I mean, I think
I have a kind of, sorry, go ahead.
I mean, even the improvements in the non-supersymmetric case, like on this slide at the top, and, it's not affecting conservation of the stress tensor or any physical charge at the end. So is it something that?
But I would object to such a thing. I mean, if you were telling me that you had a stress, like an Einstein equation, where the right-hand side is the thing that, appears in the top line, then I would object to, there being an ambiguity to it. Even though it's still a conserved quantity, after you add this extra term, the Einstein equation would couple directly to the, components of the stress energy, not its gradients.
Might be related to a field redefinition, though. I mean, if you say the metric couples to this object on the right side, you may be able to define a new metric G twiddle, which is a function of, I guess, G and maybe the scalar U. You may be able to do a field redefinition with the property that G twiddle couples directly to T and not to this object. And then you would say that, oh, well, you've just written Einstein gravity coupled to the usual stress energy, but with a strange notion of metric, right?
Yeah, that I don't think that would be the case, but I guess I don't have an argument off. I mean, it's very important, I think, in gravity that the stress energy be, unique. Otherwise, it's the starting point. It's hard to get off the ground.
Mm-hmm. Yeah, I'm not sure. I mean, I agree that the Hilbert definition is unique, but it's not immediately clear to me what, from the gravity context, if you took this, Well, I guess you could at least get a cosmological constant out of this by choosing U appropriately so that these things were constants, but
Right. Yeah, and that would you could not absorb that into the metric in
yeah.
a way that, yeah, as you were just saying.
Yeah, I guess that's, okay, you're right. Yeah, I'm not sure then.
Could there be like some choice that I know? Okay, I guess this comes in two questions. The first is are there energy conditions like there are for normal stress tensor, but for superspace? Like, could we have ANEC for the supercurrent, and would that like pick out a special choice of this redefinitions? Like, would it be violated if you do a certain sort of change?
That's a good question. I don't know of any superspace energy conditions. I would think that even if you impose that, it would pick out only maybe a class of improvements and not not one uniquely, since it's just an inequality. But that's a good question. I don't know.
Oh, but okay, but you don't know if there are energy conditions for supergravity. I mean, like superversion.
There would certainly be some induced. If you want to impose that, like ANEC applies to the stress tensor T, the bosonic part that descends from integrating out these superfields, then that
No,
would give you.
I mean for the entire thing. Yeah, for the superfield.
For the whole thing, I have no idea. No, I haven't seen any like superspace formulations or extensions of ANEC that would include constraints on these other fields. Because you would think that, I mean, maybe you could say I could infer what such a constraint would have to be by imposing some constraints on T and then acting on T with Qs to see, okay, what does that infer about the other objects in this multiplet? But I have not seen anyone who's worked that out.
Okay. Yeah, I guess naively, it just seems like you could do one of these transformations and it wouldn't hold. I don't know. You could choose it for some, but not others.
Yeah, certainly a cosmological constant type term would affect some energy conditions, probably not null, but you know, I could probably pick another energy condition and have it not be satisfied.
I guess I would want null because this is quantum. Yeah.
Yeah. Yeah, maybe the right statement is that those energy conditions should only apply exactly to the Hilbert stress tensor and not to this object. But yeah.
And I think you also mentioned earlier in your slide you were using the Noether stress tensor, and then later you switched to the Einstein-Hilbert. Is it clear that everything would have followed if you just stuck with Einstein-Hilbert throughout?
It all would have worked with Einstein-Hilbert in all of the cases throughout. So for instance, in 0, 1, and 1, 1, we used in our paper the Nerta stress tensor, and a related paper used the Hilbert stress tensor, and they agreed. So Hilbert always works basically, but there are cases where Nerta doesn't obviously work. So for instance, if you try to use Nerta in 2, 2, you find that it doesn't give you the right deformation past leading order. You have to do improvement transformations. So in that case, it's, I think, easier to just go directly to Hilbert and study that one. So they're not always equivalent. And especially in cases with gauge theory or fermions, the Nerta current is not always obviously gauge invariant. The Nerta stress tensor need not even be symmetric in general. So there's cases where Nerta is pathological, but it seems that in every case we've looked at, the Hilbert stress tensor works, or its supersymmetric generalization works quite well.
Yeah, it also seems to me that if you wanted to generalize this to some curved space-time, you would have to use, you know, then the Hilbert one, the stress tensor.
Yes, I think that's right. Although, yeah, Tbar on curved spaces comes with its own set of ambiguities, but I agree. You would probably have to use Hilbert in that context.
I don't know, is this running late? I have one more question. But this is about, I guess, Umang's talk, which I missed, which is that the flat space limit gives you a momentum dependent phase.
Yeah, the CDD factor thing.
So, so I'm assuming he was looking at like plane wave type situations and got this momentum dependent phase.
Yeah, this I think the Dubovsky type argument didn't rely on particular like constructing wave packets or plane waves or things like that. It was from a gravitational dressing type argument, but
Mhm.
it would be true. I think that argument implies indeed that if you just scattered, say, plane wave states, I don't know, take a free boson for instance, and scatter plane waves, then they would just pick up this, you know, e to the I p I p j theta ij or whatever type factor.
I see. So it sounds like some wave packet will have a non-trivial effect, right? Because if I integrate over p's.
Right. Yeah, I think you would be able to see this right for arbitrary wave packets or plane waves or something like that. I mean, it's
So like it's a pure phase for plane waves, but if it's but it sounds like maybe some aggregate, if you make a wave packet with some envelope function or whatever in P, then you would get a non-trivial effect. Is that right? Or no, am I misinterpreting the result?
I think that's right, because this is in the S matrix. So the S matrix, so the thing you would use to get the amplitudes would be like e to the I,
Yeah.
I think something like this, and then times the old one, I guess. And indeed, yeah, I guess, okay, so you're saying for constant P, this would just be an overall phase, but if you have a wave packet with different P's, then you could detect interference between the phase factors at different momenta. So,
Yeah. So I
yes.
guess I was told that it's like a trivial result, but this seems non-trivial to me. Or am I just missing something?
No, I don't think it's trivial. So this is an effect. I guess it's trivial in the sense that in infinite volume, Tbar is locally a total derivative. So the reason why you get a non-trivial effect that's detectable when you look at the S matrix is that morally you're going out to the boundary of your infinite volume space, right? Because you're preparing, you know, wave packets in the infinite past and then scattering them. So in some sense, you're accessing the boundary of the space, which is why even though Tbar locally looks like a total derivative using the Cardy argument, you can still see this effect if you go very far away. But this kind of thing would, I guess, die away when you look at kind of local measurements, because it's really just kind of the going to the far past and far future that lets you access it.
I see.
Okay. I guess I can stop the recording if there are any more questions.